Hello, hi Claire. How are you?
Good, how are you?
Good. Joseph, okay, first of all, can you tell me, do you have any doubt from last class?
Oh no.
Okay. We were discussing about the antennas, right?
Yeah.
Okay. Today we will see more about them. Okay.
Hmm.
Let me know once my screen is visible to you.
Yeah, it's visible.
Okay. 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 Okay, today we will start with antenna again. Okay.
Hmm.
Reciprocity theorem we will see. Then we will see some of the couple of the questions. So antenna gain, what do you mean by antenna gain? We define antenna gain with respect to a isotropic antenna. Suppose whatever the power, first of all, what is isotropic antenna? Isotropic antenna is an ideal antenna, okay, which radiates in equally in all direction. Suppose this is our antenna, and if it radiates equally in all direction, then that antenna is known as isotropic antenna. Okay. So and isotropic antenna is also known as reference antenna. Okay. So with a reference parameter, we are measuring the gain of another antenna. Okay, and that
Hmm.
being defined as antenna gain, power density from the antenna, from this antenna with power density from an isotropic antenna. Okay.
Hmm.
If the direction of gain is not specified, then it is the gain in the direction of maximum radiation. Okay, that's okay. Okay. Antenna gain. Now we will define the directivity. What is directivity of antenna? Antenna. First of all, I will just define in this equation power density from an isotropic antenna and power density from the antenna. Okay,
Hmm.
this is being defined as this is okay, and this is power density from an isotropic antenna divided by 4. So gain of antenna is defined as 4 pi u theta phi, okay, divided by 40. This is gain. And what is directivity? Directivity is the measures that the concentration of maximum power in a direction. It is the maximum gain that we are having from an antenna in a particular direction, that is known as directivity of antenna. So directivity can be defined as this one, and this should be maximum, and that will be give our directivity. Okay, and that will be u theta phi max divided by u max. U. This is directivity. So why that directivity is important? Because in our system we are interested to the antennas which are directional. So directional
Mm-hmm.
antenna means that if we, and suppose you need to understand here, suppose we have antenna, okay, and it is capable of radiating equally in all direction, but we want a antenna that should be capable to radiate in this direction only, and maximum radiation should be in this direction. So that property of antenna is known as this directivity of antenna. Okay,
Mm-hmm.
that's why directivity is quite important for us. Okay,
Mm-hmm.
just like we studied, I think we discussed in our last class about a torch that being focused on a particular object. So it will give radiation in a particular direction only. So in that particular direction, the radiation will be maximum. So that in that way we can define it. Okay. Now,
Mm-hmm.
see some couple of more thing about the antenna. Antenna aperture. Okay. When we discuss any link, when I'm saying that any link means that suppose we have a transmitting system and we have a receiving system. Suppose this is our transmitting system and we have a receiving system. In the receiving system, at the start we will have an antenna. Okay, so for a receiver antenna aperture parameter is quite useful for us, and we should know that what should be the aperture of the antenna. Aperture of antenna allows us or helps in calculating that how much how much radiation of the signal that being radiated will be absorbed by this antenna. Okay, so effective aperture.
Okay, so aperture is how much signal will be absorbed by the receiver.
Right. Suppose what happens that, let me make it suppose this is the PT. Okay, power transmitted from air, and this PT will be multiplied with the gain of this antenna. Okay, so at here I will get PTGT. Okay, but here after that, here our radiation power will be for PTGT get to antenna. Okay, but but this antenna is receiving this amount of power. Okay, this much of signal, but among this signal, how much of the signal can be intercepted by the antenna
Mm-hmm.
and it will send to the receiver? That will be depending upon A into EA. That is the aperture of antenna, and this is nothing but known as collector area of antenna. Are you getting the concept or not?
Yeah, yeah.
Okay, this is nothing but the collector area of the antenna. So how this antenna is sharp? Okay, so that is the aperture of antenna. Okay, and power collected at there will be proportional to this aperture. Okay,
Mm-hmm.
understood. So power collected or received at receiver collected or received at receiver will be PTGT 4 pi d square into aperture of the antenna, aperture of the receiver antenna. That is the aperture. Okay. So
Mm-hmm.
So aperture of the antenna is a physical parameter. Okay, effective aperture is quite important parameter of it. It's not like that. Whatever and suppose we have this much big antenna. Okay, so it doesn't mean that its aperture will be quite that much will be power intercepted by the antenna. No, there is a term effective aperture. Effective aperture means how much how much this power being absorbed by this antenna. Okay, and aperture antenna formula is A equal to lambda square 4 pi into K. Okay,
Mm-hmm.
this is the aperture antenna formula. Okay, so you have to remember all of those things. Okay, okay.
Mm-hmm.
Now we have a theorem known as receive. Are you able to understand? Do you understand till this or not?
Yeah, yeah.
Okay. Now we have another thing, reciprocity theorem. Reciprocity theorem. What do you mean by reciprocity theorem? Reciprocity theorem. Suppose suppose we have a one system here and one system here, and we are sending some signal. Okay, this is our transmitting system, and this is a receiving system. We are sending some signal from here, and this is suppose PT is being sent and PR is being received there. Suppose PT being sent is 100 watt and PR being received as 10 watt. Okay. Now, suppose we have interchanged the system. It means that this system will become our PT and this system is become our PR. And even though we send 100 watt from here and we are receiving 10 watt here from here, that is meaning of a reciprocity element. Okay, so if we are interchanging the element and we are getting same result at both sides, then that is known as reciprocity element. So what is reciprocity theorem? Reciprocity theorem means that this is the reciprocity theorem. The that even after changing the antennas position, both antennas behaves like in the same way. So what does it means? What does it means in layman language? Suppose you have a two antenna. One antenna you can use as a receiver and one antenna you can use as a transmitter. So the reciprocity theorem allows you can use any of the antenna as a transmitter and any of the antenna as a receiver, and you will get the same. Are you
Mm-hmm.
getting me?
Yeah.
Okay. Antennas can work as transmitter or receiver. Okay. We can take any antennas to work as a transmitting antenna or receiving antenna. Okay. Sometimes one antenna does both at the same time. That is the duplexer. Okay. That it is serving the purpose of both antenna. Okay. Okay, that's a one good theorem that you have to remember. Okay. Okay. Do you have any doubt in the antennas parameter? We studied power density, antennas radiation, and all those things. Do you have any doubt in all those things?
No.
Till this we have studied all those parameters.
Mm-hmm.
Okay.
Yeah.
Okay. Very good. Okay. Let's play with some of the numericals of the antennas that will help us. Okay.
Mm-hmm.
And from this we will try to get more concept. Okay. Can you solve this one? I haven't given these formulas to you because my intention to use the numerical to give these data to you. Okay. Are you able to understand this question?
Yeah.
Okay. So we have a radiation resistance of an antenna that is 72 ohms. Okay. Okay. And loss resistance of antenna is 8 ohm. Okay. What is the directivity if the power gain is 16? You have to find. Okay. Can you find it? First of all, I am giving some formulas here. Okay. We have gain equal to efficiency into directivity. Okay. Gain of antenna is equal to efficiency into directivity of antenna. Okay. So we can write efficiency is defined as gain by directivity of antenna. Okay. Okay. Now I'm giving you another formula. Efficiency of antenna are being calculated as R radiation by R radiation plus R loss. Okay. This is another formula. Efficiency of antenna are being calculated by radiation resistance divided by radiation resistance plus loss. Now you try to solve this. Can you answer these questions?
Just a second.
You just solve it. Just 1 minute I am giving you. Please try to solve it.
It is 17.7. Hello?
Sorry,
Is
how
it
much you calculated efficiency?
17.78?
No, efficiency is 0.8, right? 80%.
Oh, but it says what is directivity?
Okay, you are telling that directivity. Directivity will be gained by efficiency. That will be 17.7. Okay, very good. Okay, so have a note down of these formulas. That will be quite good for you. Okay, I will be just trying to go with numericals to catch up these formulas. Okay. Okay. Do you have any doubt? Anything to ask me?
No.
Okay. You will see very Calculate maximum effective aperture area of an antenna which is operating in a wavelength of 2 meter and has a directivity of 100. Can you find it? Maximum aperture.
What are the formulas again for aperture?
Yeah, I have given you formulas earlier that aperture area is lambda square by 4 pi into gain. Okay. And suppose efficiency is not given, then you can use the formula as directly gain. You can assume that efficiency is 100% and gain is gain equal to directivity. Okay. Because they are asking maximum effective aperture area. Okay. So for maximum effective aperture area, gain will be equal to directivity of that antenna. Okay. Any doubt?
No.
So can you find it?
To 31.83.
Okay. I'm not going to calculate it. You just calculate, put lambda equal to 2 square into 4 pi into 100. Okay.
Is
It
there
means
any
that 100.
is there any more like harder questions that would be in the exam in this?
Yeah. I'm checking with those harder question. Okay. Okay. Take up one big question. Okay.
Yeah.
A transmitting and receiving antennas are separated by a distance are separated by a distance of 200, okay, 1200 lambda and have directivity gain of 25 dB and 18 dB if 5 nanowatt of power is to be received. Calculate the minimum transmitted power. Okay, you have to find the minimum transmitted power. Are you getting it what I wrote?
Yeah, I just can't remember all the formulas. No, gosh.
Okay, give a try.
Can you try? Can you do
Sorry?
it?
Yeah,
Uh,
sure. Give me a moment. See what we studied, that power transmitted by 4 pi d square into gain of antenna into aperture area equal to power received. This is or not. Okay. We have a directivity gain as a 25 dB and 18 dB. You have to calculate, you have to convert into the normal form. Okay. So, and we know A equal to lambda square 4 pi and into gain of the receiving antenna. So, power PT will be PR into 4 pi d square divided by GT into A, and that will be PR 4 pi d square GT, and in respect of this one we will write lambda square by 4 pi into GR. This will become PT PR GT GR into 4 pi d by lambda square. Now can you try it? Now can you try it?
okay. Is PT the minimum transmitted power?
Yeah, PT is the transmitted power that is our interest. Okay. Okay.
What's the gain?
Okay. Are you able to find, because you have to convert it into first the directivity again into normal form. Okay, because 10 log GT will be 25 dB
Okay.
and 10 log GR will be 18 dB. You know how to convert it into these ones?
Yeah. You just what's 25 and 18? I don't see in the
Sorry?
question. What's
Sorry?
tw what's 25 and
What
18?
is
What's
5
25 and
and sorry? Can you repeat it? Which one?
okay, never mind.
Separated by 200 lambda.
Like how do we know which one is GT and which one is GR?
Yeah. You can. There is no requirement at which one GT. You can take it is a GT and it is a GR. There's no because both are used as a GT GR, right?
Mm,
Both are being multiplied. So there is nothing such thing like that. Wait.
I forgot how to convert that on the calculator.
Hello.
I forgot how to convert that on the calculator.
Okay, you can check it, right? Yeah, you can see, but these things you have to know, right? 10 log GT is 25 dB, right? then you can write log GT is equal to 2.5 dB. Okay. Then GT will be 10 raised to 2.5.
Okay. 10 to the power of
Okay.
2.
Yeah, 10 to the power 2.5.
Okay. Okay.
Okay.
Yeah.
See, I am seeing your question. Which one? 2015 paper. We have a question of given the radiation resistance of a quarter wavelength dipole antenna is 73, and what is radiation resistance of a quarter wave monopole above perfectly conductive graph? Okay. We have some another question also, frequency synthesizer. We have question number D there, which will use this formula. We have a question number D in your paper. There they have given you a radio transmitter.
Which year is this?
This is 2015-16
Okay.
is being designed. Receiver antenna again and what is transmitter power? Are you able to see the question, or do I need to write?
No, I can see.
Okay. Can see and you can try. Okay, are you able to understand the question? How you will solve it, right? And can we move ahead?
Yeah. Yeah.
Okay. Okay. We will slowly we will jump to the good problem. Okay,
Okay.
because we have many things in the antenna to cover.
Okay. I have some more like lecture slides that I'm gonna send today as well.
Sorry,
So
can you repeat it?
I have some more like lecture slides that I will send to you today, so you can like
Yeah, yeah, sure. That will be quite helpful for me
so you
to
can.
understand how your professor will be designing the question. Okay, that will be quite helpful for me. Okay. Okay, I am just giving. There are some term EIRP. EIRP means effective isotropic radiated radiated power, and this EIRP formula is PTGT. Okay, this is PTGT. So in your some question they can ask you what is PTGT. You can tell them.
Mhm.
Okay,
Yeah.
and one this is the EIRP, and one is signal noise power. Okay, that
Mhm.
being equal to signal to noise ratio, unit power received and noise received. Because what happened that when you send some signal from transmitter to an receiver antenna, with the power, with the power, you will also receive noise signal also. Okay, so the one of the parameter of our receiver is power received by noise received, that we have to calculate always. Okay.
Mhm.
Okay, got it? Any doubt in this?
No, good.
Okay. Okay, let's see what else we can cover more. Yeah, okay. Now we will see radio wave propagation. Propagation, okay?
Mm-hmm.
Okay.
Mm-hmm.
See, what happens, suppose this is one, this is earth and this is transmitter, okay? This is transmitter. This is receiver. Satellite transmitter and satellite receiver. And this is uplink and this is our satellite, okay? This is our satellite. So what happening? The signal being sent from this transmitter and it will go to the receiver. The signal will be uplink. It means that we are sending the signal, and after that the signal will be converted back, and it will be down converted and will receive here. Okay.
Mm-hmm.
And this is the in this way we are communicating in satellite communication. Our transmitter antenna sending this signal. Okay, if suppose I want to communicate with two places. Okay, so what happens in the satellite communication? We send signal to the satellite, and satellite will resend the signal to the receiver. Okay, in this way satellite communication happens. Okay, so one clear path from transmit antenna to receive antenna. Okay, no obstruction of attenuation along the path, no reflection from other object. We are not having any reflection, we are not having anything, and we can have the communication between both of them. Okay, now we have uplink and downlink. Downlink term, what is uplink? Uplink is the uplink frequency. Okay, and usually uplink frequency and downlink frequencies are different, and uplink frequency is always greater than downlink frequency. Uplink frequency always greater than downlink frequency, because of the attenuation. We can control the attenuation at the ground station, but we can't control the attenuation of the at the at the transmitter station. So basically due to this we can control it. Okay, this is in this way the communication in happening in satellite communication. But there are other way of happening the of the communication. right? Are you getting me? We can send signal if these both wanted to communicate with each other. There the satellite is a medium. We are sending the signal and satellite are intercepting it, and receiver will take up those signal that being received that will be transmitted by the satellite. But we have other thing also. This is earth curvature. Okay, this is curvature of earth. Okay, so we can have one antenna here and one antenna here. We can directly communicate with each other. Okay, but earth is not flat. Earth is not flat. So suppose if this distance is r, but actually what is happening, since earth is not flat, the signal are being transmitted from this to this, because earth is not flat. Suppose this is our one antenna, this is our antenna, and I want to transmit to communicate with them. In free space, we can communicate, and we can tell that d is the distance between them. So suppose we tell that r is the distance between them. Okay, but that is not the case, because earth is flat in shape. It is in this form. Okay, so r is not the distance between two antenna, d is the distance between two antenna, and that we have to calculate. Suppose radius of the earth is 6.378 into 10 to the power 6 meter. Okay, then we have to calculate that distance from the antenna at height h, and this distance is known as distance of horizon. Okay, and that is known as d equal to 2 into r h, and this is h height of the antenna. Okay, are you getting me?
Mhm.
Are you getting me or not?
Yeah.
Okay. Okay. Okay, we will see some propagation time. Okay, now it's time to study some propagation. Okay,
Mhm.
different RF radio propagation. One is, how many more slide do you have on this topic?
Um, just a second. So I think the last thing I sent was
You say you sent it only one slide.
yeah, but I combined them all together. So I think it was frequency synthesis was like the last. So I have transmitter and noise.
Okay.
I will send. Did you check when those slides that I sent? Did you check all of the topics inside?
Okay. Those slides were combined slide, right?
What?
The slide that you sent it earlier was a combined slide,
Yeah, yeah. It was just
introduction type.
yeah.
Okay. Do you have the
So
individual slides also?
those slides they're not just introduction. I just combined all of the because we have by weeks, you know.
Okay. 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 And you have two, three more slides, right?
Yeah, I have three more. Yeah.
Okay. Yeah. Please send it by today,
Yeah, yeah.
before tomorrow class. Okay.
I will send right after this.
Yeah. 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 Okay. I will start with ground wave propagation. I will explain. Actually, what happens, you must be also knowing that we have different frequencies at which communications being happening, right? So ground wave propagation basically happen between 30 kilohertz to 2 megahertz. Okay. And sky wave communication basically happen between 2 megahertz to 30 megahertz. Okay. And we have space wave communication above 30 megahertz. Okay. So for different frequency band, we are having different frequency or different wave pro propagation of wave. Okay. Ground wave propagation, sky wave propagation, space wave propagation. Okay. In ground wave propagation, what happens? What happens at ground wave propagation? It is also known as surface wave propagation. Okay. Also known as surface wave propagation. Okay. Ground wave is a wave that guided along the surface of the earth of an electromagnetic wave. Okay. And this is surface. Okay. Surface of the wave. So what happened in the ground wave? Ground wave, the communication being happening along the surface of the earth. One transmitter here, one receiver here, and the communication being happening along the surface of that. It's not like that we are sending the signal to the satellite and it being received here. It's not like that. It's happening along the surface of the earth. Okay. Ground wave is a wave that is guided along the surface of the earth as an electromagnetic wave. Okay. Ground wave permits the propagation along the curvature of that. Along the curvature of that, it happens. This mode of propagation exists when transmitting antenna and receiving antenna are close to each other. Suppose we have transmitting antenna and receive antenna that are very close to each other, then we can have the ground wave propagation, okay, which travel with the wave and okay. Okay. When ground wave moves over the earth, the energy of the surface decreases due to processes of absorption. Okay. What happens in the ground wave propagation as the signal moves, the signal energies get reduced because of the absorption of the energy. Okay. The energy of the surface wave decreases. Whatever the signal that we are sending transmitted to here, that signal will get decrease and it will decrease, okay, due to absorption. So and in ground wave absorption is more, absorption increases, okay. And the thing is that in here the attenuation increases with frequency, increases with when frequency is increasing. Okay. So that's why the ground wave is restricted from 2 megahertz to 30 megahertz to 2 megahertz, is being restricted to only 2 megahertz. Okay. So that is a disadvantage. If we are moving to the higher frequency, ground wave propagation are being decreased. That is one of the major disadvantage. Up to 2 megahertz we can have the ground wave. Okay, because at higher frequency ground wave will be less. Okay. Now I'm giving you a formula of electric field strength. Okay. At a desired, no, that's not useful here. Okay. The thing useful here is that ground wave is being used for ship to ship communication and AM broadcasting. It being used for ship to ship communication and air and used in ship to ship and AM broadcasting. Ship to ship and AM broadcasting. Okay. After that ground wave communication, we have sky wave. Okay. Sky wave propagation happens at medium and high frequency, and it is used for long distance radio communication. It happens for more than 2 megahertz to 30 megahertz, and it happens for long distance radio communication. In this propagation, electromagnetic wave reach the receiving point after reflection from the region of the upper atmosphere called ionosphere. Okay, suppose this is our antenna. So the signal being reflected from the ionosphere and it being received here. Okay. Here the reflection of a signal are happening. Okay. Uh, this is the this is the ionosphere. As we move above that, above the Earth's surface, we have a layer that is known as ionosphere. We have a troposphere at mesosphere. We have a one layer that is known as ionosphere, from where these signals will get reflected back, and we are receiving these signal. Okay. Ionosphere is a layer that are 50 kilometers above 52 ionosphere present between 50 to 400 kilometers. Okay. This is the skywave communication. Okay. Skywave communication. And and the skywave communication, we are increasing the frequency. I'm giving some formulas here of skywave communication. Actually, what happens in our ionosphere, this is suppose you think this is ionosphere. This is ionosphere. Ionosphere made up of different layer of the layer. Okay. Different layer. It means that we have a different refractive indexes. Due to change in the refractive indexes, the reflection of the signal is happening. Okay. Due to change in the refractive index of the ionosphere, the change that this signal reflection is being happening. Okay. See, you can see here, I'm just drawing it in a good way. This is our transmitter. If you'll see, this type of figure is given in your questions in some of the paper I saw. This is layer of, this is ionosphere. Okay. Ionosphere. And this is between 50 this is between 50 to 150 kilometer above the Earth's surface. Ionosphere is 15 to 50 to 400 kilometer above the Earth's surface. 50 to 400 kilometer. Okay. So what happens? This transmitter sends the signal and it reflected from there, and it come back to the receiver. In this way, the communication being happening. So the important parameter to consider here is one critical angle. Okay. So critical angle is sine theta c equal to 1 by 81 f square. Okay. And we can find the critical frequency here also. Critical frequency is a maximum frequency that can be reflected by an ionosphere when this theta I is equal to 0. When at a vertical incidence, when theta I equal to 0, our refractive index will become sine theta I y sine theta r and equal to 0, and it will become it should be 1 by 80 into fc, and our critical frequency will become 9 under root n max. This is the critical frequency definition. Okay. It means that critical frequency and n max is the ionization density. N max is the ionization density, and it depends upon the sun. Okay. This is the critical frequency definition. Critical frequency is what? Critical frequency, that maximum frequency that can be reflected by an atmosphere. After this frequency, the signal will be lost in the atmosphere. We can't, if we send a signal above this, we cannot receive that signal back. That signal will be lost. So that's why these parameters are quite useful and quite important for us, critical frequency and all those parameters. Are you getting me? Do you have any doubt?
I get it.
Okay. Another important thing is that maximum usable frequency. Okay. Maximum usable frequency. Maximum usable frequency, that is the maximum frequency that we can use to provide communication between 2 points on Earth. Okay. It is maximum frequency that can be used to provide communication between 2 points on Earth by given ionosphere layer. Okay. And that being defined as maximum usable frequency is FC sec theta I, where FC is a critical frequency and theta I is the incident angle. Okay. Any doubt in maximum usable frequency? Any doubt,
No.
Clara? Okay. Okay, we can stop here today. Okay.
Yeah.
And please send your all these slides, because that will be
Yes.
useful for both of us, so that we can move in that way. So
Yeah.
our so that our directivity should increase. We should focus in that area only, right? We
Yeah.
should not focus in every area. We
Okay.
have to increase. We have to be a directive antenna,
Yeah.
not a radiating antenna. Yeah.
Just follow like the slides that I sent, because that's the
Yeah, but that one is a quite shorter one, right? So I'm not getting that in which depth they have followed you, right? That's the
Okay.
issue. Because
Which
if you see the slides and if you see some of your paper, they are quite different. That is my point.
in what sense are they different?
Different means that there are many other things. They have taken here very in shorter version. So that's why I am asking you, if you have more content, you can give me. Okay.
No, no. So I don't know. So the slides that I sent, that's our lectures. So that's what our professor shows us in lectures.
Okay. And the slide that you will send now, what will include that?
It's the same thing. It's just more, because
Yeah. Okay,
it's
okay,
the.
no issue, no issue. I want to,
But
because
I
few
think obviously
their paper, yeah,
the
tell me.
like obviously I like to follow the lecture slides just to have like you know a outline of what to do. But exam is kind of the most important part. So uh,
Right. That's why my focus is also I'm going in that pattern also. You
okay,
will
okay.
see that
Especially
reciprocative theorem.
especially the last two exams, like 2022 and
Yeah. That's right. Because other
uh,
other things is quite straightforward.
yeah,
Last
yeah.
1 year we have
Those are
to, that's why I wanted to see your that descriptive slide, that elaborated slides, so that we can have a more conclusion. Okay.
it's just important that I can do the exam. So anything that you see that's on the exam, like type of
Right,
question.
right, right.
Okay, thank you so much. I'll send now.
Yeah. Yeah. You can send me now. Okay, thank you.
Bye. See you tomorrow.
Bye. Bye. See you tomorrow.